In this video, we're going to talk about Newton's universal law of gravitation. Now, the law of universal gravitation allows us to calculate the gravitational force between any two objects. It can be between stars and planets. It can be between atoms and molecules. The universal law of gravitation only depends on mass and the distance between our objects. So the gravitational force equation, or the universal law of gravitation, has the gravitational force constant. So this G here is called the gravitational force constant, and it has a value of 6.67 times 10 to the negative 11. It is a very, very small constant. And then R is the distance between the centers of mass of each object in meters. So right here, we're looking at the Earth and the Moon. And so it's not the distance between the surfaces of our two objects. It has to go all the way to the very center of mass. So that distance has to go to the center of mass. And then it depends on the mass of each object in kilograms. So we have the mass of, say, this one would be the Earth, and this one could be the Moon. It doesn't matter which is 1 and which is 2. So let's go ahead and do an example using the Earth and the Moon, and we're going to find out what is the gravitational force between the Earth and the Moon. So I have down here the mass of the Earth, the mass of the Moon, and the distance between the centers of the Earth and the Moon. So I'm going to take these numbers and I'm going to plug them into this equation. Now, this is a lot of writing, so I did go ahead and type these in. So this is what it looks like when I put them all together. And then I'm going to do all of the math in the calculator, and be careful because of the scientific notation. You need to be careful. Make sure you do things in pieces so you don't make a mistake. But the answer you would get is 1.99 times 10 to the 20. Now that is that many newtons. It is a huge number. It's a big enough number that it doesn't necessarily mean that much to us. But this is the force that's required to keep the moon moving in a circle or moving in orbit around the Earth. So when we talk about the Earth and the moon in orbit, the Earth's gravitational field is what causes the moon to accelerate towards the Earth. The moon's gravitational field causes the Earth to accelerate towards the moon. The gravitational force between our two objects is subject to Newton's third law. So according to Newton's third law, the force of the Earth pulling on the moon is equal in magnitude but opposite in direction to the force of the moon pulling on the Earth. So the Earth and moon are pulling on each other with exactly the same force, it's just in the opposite direction. So let's do a calculation. Another example, we want to know what is the gravitational force between the Earth and a 1 kilogram apple. So we have an apple sitting on the surface of the Earth, and obviously this is not even close to scale. And to find the gravitational force between the apple and the Earth, we have to have the distance, which is going to be the radius of the Earth, the distance from the center of the Earth to the surface where the apple is. So here's the mass of the Earth, the radius of the Earth, and our apple is 1 kilogram. Again, I have already typed in the numbers, so this is what it looks like when we plug everything in. And when I do the calculation, I get 9.8 newtons. Now this number should look a little bit familiar. Now remember, when we see F sub g, we have been looking at F sub g as the weight force. So F sub g is equal to mg. And if I say that my 9.8 newtons is my weight force, my mass of my apple was 1 kilogram. I can solve for little g, which was our acceleration due to gravity. I'm going to divide by 1 kilogram, and little g is equal to 9.8 newtons per kilogram. Now, if I mess with these, my newtons in kilograms, this is the same thing as 9.8 meters per second squared. This is that acceleration due to gravity. And in the previous slide, you might have noticed that term that I skimmed past quickly of gravitational field. Well, little g is what's known as the gravitational field strength, and it is the strength of Earth's gravitational field at the surface of the Earth. Don't worry about it too much right now. We'll talk a little bit more about it tomorrow. And more about it later on in the year. But a quick thing about the field strength. At the surface of the Earth, there are 9.8 newtons of force pulling on every single kilogram of mass. That is what we call the field strength, the Earth's field strength at the surface. And the moon has a field strength at its surface that's going to be smaller than the Earth's. And that field extends out effectively forever, but it gets smaller as it gets farther away from the center of mass. So those were basic calculations on basic examples of how you do calculations with the full law of gravitation. But many, many times when we do these problems, we want to determine changes in relationships based on just changing a variable. So for example, in the example problem about the gravitational force between the Earth and the Moon, how would the gravitational force change if we just doubled one of the masses? We just doubled the mass of the Moon. Well, I could go back to the problem and I could find the mass of the Moon. I could multiply it by 2, and in the problem I could multiply it by 2 and do all of my calculations. Once I got my new answer, I would take my new answer and divide by my original answer and find out what the factor was. But there's a simpler way we can do that. We can use something that we call the one-to-one rule. So the one-to-one rule allows us to determine how changing a single or even multiple variables affects other variables in an equation. What we do is we take our equation and we replace all of the variables and constants with a 1, leaving all the math. So what that means is G is a 1, and it's being multiplied times 1 for our mass 1, 1 for mass 2, divide by 1 for the radius squared. So that's where we leave the math. We have the we have the multiplication, the division, and the exponent. Now, if I work all this out with all these ones here, I'm going to get 1. So this is my original gravitational force. That's the original strength of my force. Now, what I'm going to do down here is I'm going to replace the variable I'm changing with the factor by which I'm changing it. So I'm doubling the mass of the moon. So I'm going to put in 1 for G, 1 for M1, and I'm doubling M2 divided by the radius squared of 1. If I do the math now, I get 2. My new force is 2 times my original force. So without doing all the rest of the math, I can find that by doubling the mass, I double the force. Let's try a couple of more examples. So how would the gravitational force change if we doubled the distance between the centers of mass? So this time we have our 1 times 1 times 1 divided by 1 squared. And that'll equal 1. So now it's 1 times 1 times 1. What's changing is my radius. It's doubled, but I have to square it. So when I do the math, it's going to be 1/4. So my new force is going to be 1/4 of my original weight force. On this one, we are going to triple the distance and quadruple a mass. So it's 1 times, and it doesn't matter which one I do, so 1 times 4 divided by 3 squared. So that's going to be 4 divided by 9. So my new force is 4/9 of my original. So we can do this with any equation. It's just easiest to explain it with the weight force. So go ahead and work on your practice problems.